Okay, let's get started. So over the last 4 weeks, we have been building up background in CPU, memory, assembly language, C language, and finally this week we are going to dive into the operating system. Most operating systems today they are developed in the C programming language and also a little bit of assembly. That's why we were learning those background. So this week, we're mainly talking about the process, but we will revisit this concept and the implementation of a process in this semester, because this is a core part, a core abstraction of operating system. So we will first talk about the concept of process. We will talk about the executable file format, especially ELF, how ELF files are loaded into memory and become a process. And we're going to learn how OS timeshare the CPU for different processes. So this is basically the concept of virtualization. So many of you heard about the concept of virtualization. You have been using VMware, VBox, VirtualBox, those kind. But that is also another level of virtualization. So today we are going to talk about just the virtualized CPU at the process level. So OS already have been doing that for us for 40, 50 years. Then we will talk about the mechanisms to actually switch different processes. We're going to look at some source code of x86 to do that. Like I discussed in the very first class, so the OS sits in the middle, basically between the hardware and the applications. So applications, they run at, we call user land. So they run at the ring 3 level of the CPU. Then the operating system run at the ring 0 of the CPU, which is the privilege level of the CPU, just above the hardware. So OS is a very good example of the concept of virtualization and also abstraction. So learning how an OS is designed and implemented will help you create other kinds of middleware in a computer system. So browser is a middleware. On browser, you run JavaScript, you run WebAssembly, and the browser runs on top of OS. So browser is also a middleware. So blockchain is also a middleware. On top of blockchain, you run all kinds of smart contract. And below that, you have blockchain. So everything can be considered as a middleware. Even hardware itself, it can be considered as a middleware on top of physics world and below OS. But OS is typically the one we learn, and it gives you a lot of ideas to how to implement other middleware, no matter which layer of the computer system it is. So for OS, we try to hide different features and interfaces of hardware, because different hardware, they are going to provide us with many different interface and features. Microphone, the screen, the keyboard, the mouse, all of them have different interface. Not only user interface, but also the computer interface, they are different. And also they provide different features. But OS needs to provide some kind of abstraction to the upper layer application. So when you develop an application, it's not that difficult. You don't have to think about all the different features of the hardware. On the other hand, hardware is very limited. They only have very limited resources. So how can we run so many different applications on one operating system with very limited resources? Then we need an illusion. We provide different applications, different processes, an illusion that they have full control of the whole computer, even if they're not, because hundreds of applications, hundreds of processes, they're actually sharing the same hardware, right? So this illusion is created by the concept of virtualization here. So in particular, in this class, we look at how OS provides CPU virtualization at the process level. So this week, there are several chapters from the book Operating Systems, 3 Easy Pieces for you to read. So basically, you should read chapter 3 through chapter 6. So this book is called 3 Easy Pieces. So they divide operating systems into 3 pieces. One is virtualization, another one is concurrency, and persistent. So virtualization is mainly about CPU and memory. Concurrency is about running many different processes on the same computer or CPU. Persistent is about hard disk, file system, those things. So we are going to cover all of them. So the book is free online. If you want to get a hard copy, you can get one from Amazon. So in particular, you are going to read those chapters this week. So all of those chapters fall under the piece of virtualization. You're going to read the processes, process API. So those are basically the interface OS provides for the different processes. Usually include system calls, which we will talk about Thursday. Then there is another concept called direct execution. Basically, no matter we're talking about OS or different applications, they consist of code, right? Code are just the CPU instructions. User-land applications run those instructions at a special CPU level called the ring 3 or user mode. Then the OS runs those code at a different level. It's a privilege level, ring 0. But no matter you are running a process or you're running an OS, you are directly executing those instructions on top of the CPU. The CPU is executing that. So this is different from you are running a Java program or a Python program because they run on top of a virtual machine, and that virtual machine eventually interpret or compile or translate those bytecode into machine instructions. So the Java bytecode, they are not directly CPU instructions, but eventually they will be compiled or interpreted to CPU instructions. Then so from chapter 7 to chapter 10, you are not required to read them this week, but they are talking about how do we schedule different processes on the same CPU and what kind of policy and mechanism we can use. Especially this one is interesting. Chapter 10 talk about how we can schedule many applications, processes on many core CPUs. Because all the devices you are using today, it's not a single core, not a single CPU device. Even your phone has maybe 4 or 8 cores. The data center may have, those computers in data center may have 500 cores or 1,000 cores. My laptop I'm using for the class is 8 cores. Okay, so how do you schedule different processes there is also an interesting topic. So after all, what is a process? So a process is the basic unit of a program in execution. In other words, it is a running program. That's it. So you have been writing programs in assembly, in C in this class. You compile the program to a.out or any other names. So that a.out, that's a file. That's a program. That's an executable file. But it's not a process yet because it's lifeless. You are not running it on the CPU, right? So when you load that program, when you type that a.out in the terminal, when you type that, the terminal actually create a process for you. The terminal actually load that program from hard disk to the memory so the CPU can execute that program. Then that program becomes a process. So that process can interact with other processes, can interact with the operating system, can even connect to the network, the internet, can interact with remote computers. So one of the core job of a modern operating system is to create, run, and manage many processes dynamically. For example, when you type a.out, the OS will create that process, run that, And there are many other processes running on your computer at the same time, including the terminal itself. The CPU, the OS will decide how to schedule different programs to run at the same time. So on a Linux or Unix-like operating system, you can easily, or even your Mac, you can easily use commands like ps or htop or top to say how many programs, processes are running on your system. If you want to know how many programs are there, you just list them in your file system. For example, here on the left-hand side, I use the command. This is from the command ps3 actually. So ps3 shows me what kind of processes are running on my laptop and who created those processes. Like this is like room created many different child processes like that. On the let me just show one too big. Let's do a htop. So when we do a htop, we can say so many programs running on my computer right now. Let's just do the command, I guess. So htop gives us the running processes right now, and it shows you the CPU percentage, the memory usage, the priority of this process. In Linux, there is a concept called a nice value. This is a value users can set, and you can set the priority of the process by setting the nice value. This is a virtual memory this process is running. And if we check this, you can see some of the processes, they use a lot of virtual memory. So this is a 64-bit machine. If it's a 32-bit machine, the whole physical address is only 4 GB, but a 64-bit is huge. So you can see those kind of processes. This is my Chrome. This is my browser. So browser is using 1.2 GB of virtual memory, okay? My physical memory on my machine is only 32 GB, but the virtual memory this program is using is 1.2 TB, okay? So a large portion, a huge portion of that virtual memory address is not really backed up by any physical memory, okay? Then the actual physical memory this program using is only 300 megabyte. So this is called the resident memory, basically the virtual memory this process is using. Let's say also this part is shared. This is a shared physical memory with other processes. So basically 2 megabyte for this process, 120 megabytes for others. Then we have the name of the program running here. So that's basically the processes I have on my computer. If you can, so let's see how many are there. We can do a PS AUX. It will show us all the processes. It's just not interactive. So if we do a grep, oh no, let's do a word count, how many lines there. You can see on my computer right now, there are more than 300 processes running. On your laptop, probably the same thing. You have hundreds of processes running at the same time. Even if I only have 8 cores on my computer, on my CPU. So if you want to say what programs you have, one example is go to the user bin directory, and all the programs there are executable. And you also have hundreds or thousands of programs there, but they are not processed yet unless you type the name in the terminal, then they become a process. So you probably notice one thing that we see many processes, they have the same name. For example, I played a little bit of video game last night, so that's why I have a Steam here. I have Chrome here, right? I have many Chrome here. Even though my Chrome browser right now, I probably just open 1 or 2 tabs here. I opened 3 tabs here, but there are many Chrome processes here. So if you want to understand why we have so many Chrome processes, even though I only have 2-3 tabs, there is a paper talk about this design back in 2009. So I still remember this paper. That's when I started my PhD, and I was into browser security. So I was reading this paper. So this is when they started to separate browsers into different processes. So the idea, the motivation for that is mainly for security. So browsers, there are many tabs, and you are using them to visit different websites. And some of the websites could be malicious. They could have malicious JavaScript. And the malicious JavaScript will try to crash your tab. But if one tab is crashed, if they are in one process, then the whole browser will be crashed, right? So the idea is to separate them into different processes. So even if one process is crashed, the other tabs, you are still visiting other websites, you are even playing games, you are watching Netflix on other websites, they will not be interfered. So that was the idea. So this is a very nice article talking about the design of that. So we have been using this kind of design for more than 15 years. So next we talk about how we actually run a program, how we turn a program into a process. Then what kind of information the executable file, the program must have, so the OS knows how we can turn that into a process. So there have been many different executable formats. And the one we usually use for Linux and Unix systems are called L files. The a.out file is L file. And the .o file, the object file, is also an L file. In Mac, they use a different format called Mac-O, and Windows use the PE format or PE32 format, usually .exe. So the extension is .exe. In Linux, the extension doesn't really matter. So PE files usually have a magic code called the MZ. And for historical reasons, that's actually from older DOS executables. They are called MZ executables. So different format, they also have their own magic code. For L file, the magic code is at the beginning of the file. It's just called ELF. So ELF is very popular, mainly because it's open source. There is no license required to use it. That's why the Linux world, the community, we just use ELF. And the ELF was originally designed for System V. You will see this term many times in this class, System V. Even in modern Linux, if you look around, look at the code, play with the memory space, you sometimes see this word System V. So System V was a line of a commercial Unix operating system from AT&T in the 80s. Even though we're not using that commercial system anymore, Linux followed the design of Unix. And also some of the specs of Unix was open sourced. That's why we're implementing everything on top of that. So the application binary interface we've been talking about, how we should, the core E or caller, who is supposed to maintain the registers, those things, the calling conventions, they were defined in the sysv API, and also the executable format, the linkable format is also defined there. So this document is public and everyone can access that. So for L files, it has actually a very simple format. So this is a file. This is on the file system. This is not a process. So for L files, first of all, at the beginning, we have ELF headers. Then after that, we will have some program headers and also section headers. So in this class, we mainly talk about the program headers. Then we will have code and data. That's we already discussed many times. The code will go to .text section. Read-only data will be RO, read-only. Local global variables will be .data, right? Then there are also uninitialized global variables go to BSS section, right? So how about stack variables, local variables? Where do they go? Anyone remember? We talked about this last week. stack variables. Okay, so are they here? Okay, so this is a file, right? This is the executable. So the stack variables actually not here, okay? They are created when the stack is created. So you access those stack variables using an offset of the EBP or RBP, right? So they are not really here. So they don't need to be in this file. Yeah. So there are many tools we can use to read the headers or analyze L file if you want to look into an L file. One tool we can use is called readelf. And this tool is available on all Linux-based systems. For example, our code space. If you go to code space, we use assignment 3 as example. So this is my assignment 3 repo, and we already have a.out. And if we do a file tells us what kind of file it is. So we do a.out. We can say this is an L file, 64 bits. This is position independent execution executable. This is for 64-bit x86 machine. This is the ABI is system V version 1. Okay, so system V, we talk about that. This executable is dynamically linked, which means if it calls C libraries or maybe other libraries, those libraries are not in this file. Those libraries will be dynamically linked by the OS. Maybe other programs, other processes already loaded those libraries. So this program doesn't need to load that library again. And this program uses an interpreter, and this is an interpreter. That interpreter basically is a loader. The loader will actually load this program into memory. We will talk about that later. So this one is not strict. There are symbols on this program. If you do a readelf, we do a readelf all. We try to read all the headers. Then we can get a lot of output here. So first, we will have the very beginning, the header of the file. The first 16 bytes are magic numbers, and those magic numbers are just elf. This is 7F, 45, 4C in hex, that's just ELF, elf. Then it shows that this is a 64-bit L file. The ABI is system V, version 0, position independent executable, built for AMD x86 64-bit. The entry point is at this address, the offset in this file. The entry point is basically the underscore start function we talked about, or underscore start label we talked about. This is not your main function yet. This one calls the C library function, libc start main, libc start main, eventually calling main function. So this is the entry point of this program, and the start of program headers and the section headers. Then there are many headers there. So let's take a look at the program headers. First is section headers. So then we can see section headers. There are many different sections. Something here, the loader is called the interpreter. That's a loader part. Then there's the ABI tag, hash value, dynamic symbols, some strings. In this class, we focus more on program headers. So let's jump to program headers. So here, program headers defines how the OS or the loader is supposed to load this program into memory. So here, so this is the interpreter header. What is the size of it? What should be the flag for it? Readable or executable? So here, for example, this one is readable and executable. This one is only readable. Then there are many, so those should be loaded. There is even a stack section because it's a stack, it's for local variables. So we do not only just make it readable, but also writable because we're going to write to the local variables. So those are the program headers. So also we have symbols here. So symbols are basically those global variable names, function names, and you can find something familiar here, I guess. Frame dummy is a function we saw before. What else? We do not see many familiar functions here. Here, we have the main function, the underscore elite function, a label of end start. So this start could be a function. So this is the entry point. See, the start underscore start is at the offset 1040. That is marked as the header of the L file. That's the entry point of this program. Okay. So that's basically an L file. And the OS job is to load any L program into memory and create a process. There are multiple steps in that. First of all, the OS needs to place those segments from the file into memory and also load necessary dynamic libraries because some programs, they need other libraries, but they are dynamic, so they are not really in the executable file. Then it may need to move those file sections at different locations. So that's called a relocation. And also for C programs, you always need a stack. So the loader will also allocate the initial stack frame. And after all of that, need to set the program entry point to the register EIP. Okay. As soon as you set that entry point into EIP, the CPU will start executing from the entry point. So you are executing the program, not the operating system anymore. So usually the memory address looks like this. So we need to set the ESP for the stack. We also need to set an EIP to execute the program. So we will use x86 as an example to study the whole process. We are looking at the x86 code. So the background here is x86 programs are all statically linked. So they do not use any dynamic memory, dynamic library. So all the programs you compile, even the programs you are familiar with, ls, sh, they are fully statically linked into one L file. The downside of that is each of those executable need to embed their own C library there if they use C library. So if they are loaded, so both ls and sh are loaded to the memory, they are both running, then there are two copies of C library in the physical memory. That's basically a waste of memory. But x86 is a simple education operating system, so it only supports this. And in x86, we don't have a userland loader, so the OS does all the job. So OS is a loader. So later we will see that in Linux, actually Linux, the kernel doesn't do the loading job. The kernel will load something called the interpreter or loader. The loader will actually load the application. So we are going to look at the exec.c file of x86. And in that file, we basically only have one function. It's the exec function. So that function is triggered by a system call. The system call is also called exec. So when a usernet process running on x86, it makes a system call EXEC system call, or maybe there is a C wrapper for that. Eventually, the CPU will switch to privilege mode, switch to the kernel mode, and start executing that function. So the code we are looking at is actually in the kernel mode, but later we will look at the user NAND part as well. So this piece of code will basically open the ELF file itself from the file system, because it's a program, it's a file. We need to open that file from the file system, but we're not going to use program functions like open or read, because those functions are for user NAND applications. Those functions are not implemented in the kernel level. Kernel have their own functions. Then the program will read the header, specifically the program header. Look at the program header and just check if I need to load the corresponding section from the program to the memory. After that, it will allocate memory for those regions and set up a stack and eventually give the control to that program and return from kernel mode to the user NAND mode. So this is the code we are looking at. So this is the code. You can see the code is somehow similar to our main functions prototype. In main function, we have a int argc and array of char star argv. So here we also have an array of argv. So char star star basically is the same as char star argv array bracket. That's basically the same thing. But here we also have a path. So that's the path of the file, the executable, the OS is trying to load into memory. So when we reach here, we already entered from user NAND to kernel mode. So from here, this is kernel mode. So we're not going to look at this line by line. We will only look at some important lines. For example, here. So proc is a data structure to define a process. Here we have a pointer to get what is the current process running on this system. So when you type a.out on the terminal, so what is the current process? We have terminal there. You type any program, ls or a.out. What is the current process? Eventually, the OS will create a new process for you, a.out, right? But before that, what is the current process? Let's say right now we just enter the kernel, just under here. What is the current process? Do you have an answer for that? Just guess. Exactly the terminal. Okay, so terminal is a process. And when you type a.out, terminal is going to fork itself, then execute execve or exec in x86. So the current process here is the terminal, and we're going to replace that. Okay, so the exec system call basically replace the current process with a new process. And Unix-like systems, they use this design. You first, one process first fork itself, then replace itself with a new program. So there are basically two steps, fork and execve. So this design is different from Windows. In Windows, you have a system called create process. There is no separate fork and execve. So the benefit of having fork and execve is we can do piping, we can do redirection, which we will talk about later in this, not today's class, in the semester. So after that, you can say, first, this is path is the executable, right? We're going to use the name I function, this is kernel function, to find that executable. So I here means I load. That is a concept related to the file system. So we're trying to retrieve this file from the file system. So we're not using the open function because it's not available in the kernel. So if this file, the program you asked me to create a process for doesn't exist, obviously we're just going to return. Otherwise, we keep going. We're going to read this file. We're going to use read load of that file. And first, we're going to read the header of that file because it's supposed to be an ELF file, right? So we're going to check if that file has ELF magic numbers, which are the beginning 16 bytes, the ELF, those kind of things. If they do not have those magic numbers, means this is a broken ELF file or it's not an ELF file, then we will just exit. Otherwise, so this is the interesting part. We are going to check how many program headers, program sections are there. And for each of them, we are going to enter this loop. We are going to read that data section from the ELF file, and we are going to allocate a user level memory. So allocate UVM is user virtual memory for that section. Then we are going to load that file, the segment from the file to that memory. Okay, does that make sense? We have file system, have executables, ELF file. ELF file have different sections. For each section, we're going to read them and load them into physical memory. But we're going to present those physical memory as virtual memory, and we're going to make sure those virtual memories are accessible, executable at the user level. So even though this piece of code running in the kernel level, this part is because eventually the process running at the user land level. So after that, we also need to create page tables for this program. We will skip that for today. Later we will look at that. Then we will execute that program, right? So what I showed you last week, when we execute the main function, the loader, or in this case, the OS, will push the command line arguments to the stack, right? That's why in the main function, you look at argc, you can see how many command line arguments are there. You look at argv, you can see all the strings of the command line arguments. And this piece of code is actually doing that, okay? This piece of code is actually pushing those parameters onto the user stack of that program. So then later, when you enter the main function will be able to say those parameters. So after all of that, it's just going to free the old page tables and switch to userland, then just keep executing. Okay. So that is the basic idea of the loader in this case. So this is the OS implementation in x86. So those are the main functions in this process. We have the main proc function to return a pointer to the current process. There is a setup kernel virtual memory function to build a fresh kernel page table for the new process. Then there is a allocate user virtual memory function to allocate new userland memories, load the file content into userland memories, then eventually switch to the userland memory, then the program can start executing. So Linux use a different approach. x86, we saw that it's only 200, 300 lines of code. We can load an ELF file to the memory, then start executing. Linux is much more complicated. It also uses a different approach. So when you type a.out in terminal in Linux, what happens is the terminal process will also first do a fork, then do a exe cve system call, which enter the kernel, but the kernel code of that part is simpler. The kernel, the exe CVE system call, similar or equivalent to the exec we just saw. The exe CVE system call will check the header of the L file. If the file has an interpreter section or loader section, then the kernel will not do the loading itself. The kernel will load the loader, and the loader is basically in this library. .so is a static library. So the kernel will only load the library. Then the library is a userland application. Then the library will load your program into the memory, not the kernel directly doing that. Okay. So you can guess what is the benefit of doing this. Okay, that's a good point. And also, if there are errors, we're not going to crash the kernel. We're only going to crash a userland application, right? So for most of the programs we are using today, they use this approach to load. So I have a LS program in my system, and I do a LDD on this program, then I will be able to say what its interpreter. As you can see here, this is the C library. This program using this version of C library. And here is the loader or interpreter. So, and the interpreter will be loaded at this memory location. And it's this interpreter's job to load the L file into the memory. Any questions so far? Cool. Then we just saw that even on my laptop, there are more than 300 processes running at the same time. So how can the CPU run so many processes? How the machine runs so many processes at the same time? First of all, the CPU, or at least a core of a CPU, can only run one instruction at any given time. It cannot run multiple instructions at the same time. Okay. This is because the CPU use this fetch, decode, execute approach to fetch an instruction from the memory, because instructions are also stored in memory. No matter it's kernel instructions or application instructions, they are stored in memory. The CPU is going to fetch it, decode what it is, then execute it. So if your CPU has 4 cores, then it can do 4 of those cycles at one time, but it cannot do more. But we are running many more programs on that. Internally, the CPU have some other registers to help do this. So those registers have, we are not familiar with them. Those are not the RAX, RBX. Those are registers or exposed to applications or exposed to kernels. But there are some internal registers like MAR, MDR. It's called memory address register, memory data register, or current instruction registers. So those registers are internal registers. There are no instructions exposed to applications to directly manipulate those registers. But those are the cycles we need to follow here. So this is how many CPUs I have on my laptop. I do a LS CPU. I can see that I have x86 CPU. It supports 32-bit and 64-bit. The physical address space is actually only 39-bit. Virtual address is 48-bit. Even though the CPU technically can support up to 64-bit, we're not really using the full 64-bit at this moment. I have 8 CPUs on my laptop. Each of them has 2 threads. Let's ignore that part. That will make things very complicated. So just assume I only have 8 CPU here. but I'm running over 300 processes at the same time. Then the question is, how does our operating system provide the illusion of hundreds of processes running at once? You have the feeling that all of them are running at the same time, right? But I only have 8 CPUs. How do we do that? First of all, let's go back to HTOP. So in HTOP, there is another column we didn't talk about, is this column. It's called state, okay? So this column shows us the state of this process. For example, for HTOP, the current state is running. R here basically means running. S here means sleep. So at some point this is running, then you can say it's sleeping, okay? So most of those processes, they're not really running, okay? They are waiting for some data. For example, my Chrome maybe wait for some network package. And only if the network package arrives, the OS will wake it up, so it keeps running. So on my computer right now, we don't really have many running processes. Most of them are sleeping. But this also changes very fast, changes in milliseconds, and may not show it here. So in short, OS provide CPU virtualization by time sharing the CPUs among all the processes. Then each process has the illusion that it has full control of the CPU. It even has full control of the whole computer. But one CPU can only execute one instruction at one time. And that one instruction obviously only belongs to one process, okay, or kernel, right? So how do we do this? Let's say we have 8 time slots labeled from 1 to 8. Then we have 2 processes running on our system. Then we only have one CPU in this scenario. So when process 0 is running, then process 1 cannot be executed at the same time. So then we can use 2 different states to label them. So process 0, basically running, it's in the running state. Then process 1 is runnable. However, it's in ready state because it's not really running. Then process 0 uses 4 CPU cycles or time slots. And maybe after time slot 4, it's done, it finishes. So it doesn't need the CPU anymore. Then process 1 get an opportunity to execute. So this is time sharing between 2 different processes. So we need at least 2 states here, running and ready, to describe the state of the processes. However, it's also possible that the process will interact with other processes, interact with network, but the network package will come very late. So that process needs to wait there, right? The process have no data to consume. One way we can do this is we ask that process to keep checking if data is already here. So that process is still consuming CPU time. Just keep checking if data is here. Then, but however, we do not have a chance to execute other processes. So we are wasting some CPU time there, right? Then another way is we put this process into sleep, into a wait state, like what we saw in HTOP. Most of the processes there are in the sleep state. Then we have a chance to execute other processes that are ready to be executed. Right? So to do this, we introduce the third state. We can call it blocked. So in the book, it's actually called the blocked state. But in modern systems, usually this is called a sleeping state. So now we have 3 states, running, ready, and blocked. So a process is running, then the operating system may decide I want to switch to another process. Then we will schedule to another process. Then the current process turns from running to the ready or runnable state. Then later, the OS may schedule that process again. So that process go back to the running state, keep running. Then that process may send out some data or wait for some data from the network, then enter the blocked state because it has no data to consume. So it went to the blocked state. When that data comes, the OS will make that process into the ready state, ready to be scheduled. Okay, so those are the three basic states we need to describe a process. If we use x86 as example again, or Linux use a very similar structure, then we have unused state. So basically, the process has not been created yet, and we can only create limited numbers of process in this case. So there is unused state. Then used means this has been initialized, has been created, but we haven't fully loaded everything into the memory. This process is not ready to be executed. Then we have the sleeping state. Basically, is the blocked state. We are waiting for some event. Then we have a runnable state. So this process is runnable. You can run it anytime you want. Okay. And the running state, the CPU is actually currently executing code from this process. And when this process is done, the process actually enters a state called the zombie state. This is the same as Linux. Linux also have this zombie state. The idea of this is even if a process finishes execution, the parent of it may still want to analyze its return value or analyze what it has been doing there. That's why we put it into a zombie state, means it cannot execute again. However, its parent or any other process who has a permission to analyze it can still analyze its memory and everything. Yeah. So if we look at the source code, so this is the proc.h file. Proc just is process. So here, it actually defined some CPU information per CPU state, like context, segment, but that's not our focus today. We will go to proc state. So proc state is basically an enumerate structure in C programming language. So unused has a default value of 0. Used umbro has a default value of 1. Sleeping, runnable, running, and zombie. So those are the state. Then we have the proc. So this is a proc structure. So all of this is in the kernel, okay? So this is a kernel data structure for a running process, the proc structure. Let's start from here. So the last member here is char name. This is the name of this process. You do a.out, you do ls, that will be the name of this process. Then there is a iload pointer. Iload is related to file system. This is the current working directory. So this is the same concept as other Unix or Linux programs. You have a current working directory. That's what you have as a dot, right? When you do dot/a.out, the dot means the current directory. So how the program or the OS knows what the dot means for this program, that's because it is stored here, current working directory. Then we have some file pointers. So how many files are opened? We will talk about this in weeks. Killed, whether this process has been already killed. This is, I'm not sure about this one. Here we have a context. basically when you, so how does the OS provide the illusion of the provide the illusion for the processes that they have the full control of the CPU? When they run process 0, everything about process 0 is in the CPU registers. Then if we switch to process 1, then we are going to move those process 0's data out of the registers. And we're going to save it somewhere, right? We save it in something called a context. So that includes all the register information. Then we are going to load process 1 or process 2's context back into the registers, then keep executing there. So even if there is only one physical copy of the EAX, EBX, all those registers, but process 1's or process 2's value of those registers can be stored in memory. Only if we execute them, we're going to load them into memory. Then we're going to skip this one for today. There is parent process. A process is always created by another process. That's why they already have a parent. In Linux or in x86, the very first usernet process is called init or process 0, and that is created by the kernel. All other processes, they are created eventually by this init process. Then each process has an ID identifier. That's why it has a PID here. In Linux, it's a little bit more complicated. We also record the parent's PID. Then we also have the state of this process. So that's the enumeration structure we saw. Then we also have this program's page tables, where we talk about that in 2 weeks. Also the stack, the kernel stack for this process. Then also the size of the process memory. So those are the basic information the kernel maintains for any process in x86. So now we know that the operating system is going to switching different processes, but you do not really feel applications lagging, right? Even though they are sharing the CPUs. I will need you to think about this. Why is that? Then we're going to revisit this later. Okay. So the next we talk about the mechanisms or policies the OS use to switch processes. So first we talk about more like a high-level idea. Then next class we're going to look at the concrete source code of the switching. So when we switch those processes, there are so many things we need to consider. First of all, the CPU, if we only have one CPU, it can only execute one instruction. That instruction either belongs to some process or belongs to the kernel. So as long as you are running a process, the process may never give the control of the CPU back to the kernel anymore, right? Because you are running a process, you are running an application code, and your application code could be a while loop, a for loop, an infinite loop there. Then the kernel, the CPU will keep executing that infinite loop at a user land, at a process level. It may never have a chance to go back to the kernel to do anything else. So when you design OS, you need to consider that. How we make sure eventually we can go back to the OS because the applications could be malicious. We also need to consider that the cost of switching processes. Basically, we need to copy one process's context, all the registers, from the physical memory to the physical CPU. Then move another process, the running process context from the CPU to the memory. And that could be time consuming because we are copying a lot of data from the memory to the CPU. So then how often should we do this? When we do this, it will consume some, because when we are doing this, we're not really doing the actual computation, right? So there are basically 4 different approaches we can use to make sure that the CPU will not only keep executing in the usernet. We will have a chance to go back to the kernel to do something else. 4 basic approaches. The first approach is called the volunteer yielding. The idea is very simple. The application, one process, usernet process, after it finishes what it is doing, or it's halfway there, it decides that I give up the CPU. I will let other process to run. Okay. So some older operating systems actually use this approach. Even modern operating systems, we still provide this mechanism there. x86 actually didn't implement this, but Linux has this, and other operating systems also use this. A second approach is to switch during API calls to the OS. So what are the API calls to the OS? We talk about this many times. What are they called? Yeah, system calls, right? So most applications, they will make system calls. If they read file systems, they need the network. They need to go to the kernel. The kernel will do that for them. So they will make system calls. So as long as they make a system call, it gives the kernel an opportunity to execute. Then the kernel can decide, maybe I should swap this process with another process. A third one is a switch on I/O, which means like reading a file. But the switching to I/O actually is also based on system calls, so it's similar to the second one. Then the last one is about a timer interrupt. This is the most important one, and all of our operating system now implement this as well. We actually use combination of all of them. But the last one guarantees that the kernel get a chance. So there basically is a physical timer, usually inside the CPU, and you can configure the timer 1000 Hertz or 250 Hertz, which means every 1 millisecond or 4 milliseconds, this timer will fire. Okay, it will fire and interrupt. Yeah, go ahead.
It's the process, right? It's something physical.
Timer is a physical thing. It's a hardware, but usually it's inside the CPU. Yeah. Many modern CPUs, they actually have multiple timers for you to do different things. And this timer is not related to the CPU cycle. That's a different timer. Yeah. Okay. So then for, let's say, modern Linux actually set it as 250 Hertz or 1000 Hertz, which means every 1 millisecond to 4 milliseconds, the Linux kernel will get a timer interrupt. So it will interrupt whatever process is running and go to the kernel. Okay. Then the kernel have a chance to switch to other processes or do their job. So voluntary yielding, usually there is an interface called yield. Linux actually have a system call called yield to do this. x86 doesn't really have this. I was looking at the x86 code yesterday, then I find out x86 doesn't really have this. x86 have a kernel function called yield, but it didn't expose, at least the stock x86 didn't expose that to the userland to a system call. But actually it can be a good homework to expose that to userland to provide this interface. So the problem of this is, like I said, the applications, the userland process, they may misbehave. They may never yield, or they may have bugs. There is just an infinite loop bug in the program. As long as you enter there, you never get a chance to yield. Then we are going to waste a lot of the CPU, and basically your computer cannot do anything else because you only have one CPU. Then the other approach, the second approach, in the OS APIs, this is also called the interjection approach. So whenever a process makes a system call, it means we are going to enter the kernel level. We are going to execute some kernel code. Then the kernel code can do whatever we want to do. The kernel code can decide if we need to context switch to another process. And a lot of C functions, they will eventually make some system calls like printf. Printf itself is not a system call, but eventually it may make a system call like write. Basically, you're writing something to a file descriptor. That's a write system call. You can do an open socket. Socket itself is a system call. So early Apple computers actually use this approach. This is a little bit more cooperative than the previous one, right? But still, there may be problems. The applications may still have an infinite loop, so they never go into the kernel, so the kernel never have a chance to schedule. Switch on I/O is similar to the previous one, but the problem is some applications process, they may not even do any I/O operation. Let's say we are doing some very complex matrix multiplication. That doesn't require us to go to the kernel to do anything, right? Or doesn't require us to get anything from the I/O interface. So that's why we have the last approach is a timer-based approach or preemptive switching. Basically, we do not assume all of the processes or any process will voluntarily or eventually voluntarily yield the control. We need some approach to interrupt them no matter what. And the idea is to use a physical timer to give the CPU a signal. And when the CPU got that signal, CPU start to execute certain predefined code. And that code is to do context switch between different processes. Okay. So now we go back to why I do not really feel apps are lagging. Right? We're running so many processes, 400 of them, but I do not really feel they're lagging. I'm playing video games, watching Netflix at the same time, and I do not feel that, right? Why? The reason is the switch is so fast. Our human perception of this probably is, if you feel lagging, it probably is something like 100, 200 milliseconds, you can feel something. If it's faster than that, you cannot really feel it, okay? So then the idea here is we do the switching faster than that. We're running Netflix and also a video game, a browser, watching Netflix and a video game at the same time. But each of them will run 10 milliseconds, then switch to another one. Another 10 milliseconds, switch back. So the lagging here is only 10 milliseconds or fewer than that. So humans do not really feel that lagging. So like I said, in modern Linux systems, the default scheduler, the tick, the timer is set to 250 Hertz or 1000 Hertz. So the timer will fire every 4 milliseconds or 1 millisecond. That means in 1 second, there will be up to 1000 context switches between the processes. And even if on edge top, we saw that there are 400 processes on my laptop, but only maybe 10 or fewer of them are actually running. Most of them are in the sleeping stage, right? They are waiting, they are sleeping. That's why you do not really feel anything. But for some modern applications, this 4 millisecond or 1 millisecond is still too slow. Let me give you another example. When you search in Google, you type something to google.com. Then Google is supposed to return to you the search result very fast. In just maybe several milliseconds, you feel that. So first, whatever you type will go back to Google's front-end server. Then the front-end server will fire different requests to maybe hundreds of requests inside Google's data center. And those requests are going to do many different things. They are going to search your term whatever you want to search on different distributed machines, they are going to retrieve advertisement related to what you search, right? All of those. And all of those have to come back to you very quick in milliseconds, considering the round trip of the data transmission as well. So in modern data centers like that, actually we are looking for nanosecond or at least hundreds of nanosecond of data processing in those data center machines. But if those data center machines are using Linux, their context switch is only 1 millisecond. Your request arrives at, and that data center machine is already executing something. It will wait at least 1 millisecond or 4 milliseconds to serve your request. Even if your request is very small, executed in 50 nanoseconds, the whole thing, you still need to wait 4 milliseconds, 1 millisecond plus that 50 nanosecond, right? That's why we also need faster context switch for those data center machines. That's why there are a lot of research going on in that direction to make the context switch in there much faster. So in our lab, we also have a project working on related areas to make the context switch very fast, even in virtual machines. Oh, okay. So that's basically what I have for today, meaning the conceptual level. So Thursday, we're going to look at the source code of the context switch, how actually XV6 copies EXE, EAX, EBX, those registers from the memory to the register and back and forth. We still have 25 minutes, and we have a due today, right? The lab. So I will walk around to help you guys to finish that. So any questions regarding today's class? Okay, we're good? Okay, cool. Yes.